All right, starting the stream. I think that's working. Yep, all right. So welcome everyone. This is a behind the scenes where you see me work. So this is not meant to teach you anything in particular, but you're going to see my process for working. I've been doing a couple of content projects recently. And so one of them is I'm writing a book, and it's going to be an EVPN VXLAN cookbook for Arista EOS. So that'll be for people who are looking to learn EVPN VXLAN, or even if you're going to sit the Arista L3 level 3 exam, this could help out with that. So this is the process. So I've chosen to do this using using VS Code as my editing thing because I'm going to do it all in Markdown. And the idea, I would use LeanPub or something like that to publish it. I haven't figured out how exactly I'm going to publish it, so I figure I'll do the content first and then kind of figure out the rest from there. But because there's so much, technical text and configs and so forth, I'm probably going to just do everything in Markdown. One of the challenges I had in this was spell check. I'm a terrible speller, as many people will attest. And my friend's in here laughing. VS Code doesn't really have a built-in spell checker, but there's an extension you can get. So it's a rudimentary spell check. It's working enough for what I'm doing, but it's not like you would get in most other editors. It's also Friday late afternoon, and I'm enjoying a cocktail, so this could get spicy. And so the goal for the book is to just have a technical resource on doing EVPN VXLAN. I'm probably not going to charge a ton for this book, maybe like $30. Maybe not even that. I don't know. Two things. One is to learn the syntax, configuration syntax for configuring EVPN VXLAN for Arista EOS in that environment. And also as a study guide and resource for taking the Arista Level 3 exam, because it's one of the biggest parts of the Level 3 exam. Now, it's not guaranteed to be on it, but the blueprint for the Level 3 exam includes a lot of VXLAN, EVPN VXLAN. So Arista allows you to bring in study materials. It allows you to bring in, you reference blog articles and so forth. And so you can use that when you're taking the test. And so this could be a good help for that. But I will warn anyone who is thinking about sitting an exam and using like a cheat sheet like this. If you don't understand EVPN VXLAN, you're not going to pass that exam. It would be a miracle if you could, because you have to understand what the pieces do and how they work, etc. But this guide is meant to show you how to translate that into syntax. And so whenever I teach VXLAN, I have the 4 steps. So every time I've got a PowerPoint that I'm using as the for images and graphics that I'll put into there, but I'll do one here. And this is the I don't want Copilot. 4 steps to making EVPN VXLAN. Fabrics. And the first step is you have the topology. That's the typically leaf spine. How the devices are connected. So we need some sort of topology. Typically it's what we would call leaf spine. The next one is going to be the underlay. And all the underlay does is put loopbacks into routing tables. Then we have the overlay, and that loopbacks to routing tables. The overlay peers leafs with spines via MPBGP with the EVPN address family. So it's not normal. We're not routing IPv4 over the overlay. All we're doing is peering the EVPN address family so that we can exchange routes that are learned, endpoint routes. So type 2 routes, for example, the leaf learns a MAC address. It generates a type 2 route. The type 2 route gets exported or gets shared with the leafs, with the spines rather, via EVPN peering, and then it gets redistributed to the leafs. And then we have the EVPN services. So that's things like stretched VLANs, which are L2 VNIs, anycast gateways, VXLAN segments, same thing as stretched VLANs, external routed connections. So those are the 4 steps when we're creating these EVP and VXLAN fabrics, and I like to do them in order. Topology wise, most of the time that's already done and they're all plugged in. So then we start the actual configuration. We start with the underlay, overlay, and EVPN services. But we also might have the topology. It helps to know what the topology is, and I'm using Container Lab for this. So let me increase so Container Lab deploy. There we go. Nice thing about Arista is they have a very lightweight container that's a full data plane and control plane for EOS. So you get almost all the features you would get out of a physical switch. There's a couple things that are missing, but we could definitely do EVP and VXLAN and pass packets and do IRB and all that stuff. And it's relatively lightweight. I can fit 4 leafs, an external router, and 2 spines and 2 hosts. So it's like 11 devices. And I can fit that into 16 gigs of RAM with 4 CPUs, and it works just fine. I don't care about that error. So the trick for this cookbook is the cookbook's going to have configs, and I have to test to make sure the configs work. One of the things that I decided when I was writing this was I'm not going to use any AI to generate the content because this kind of stuff, AI typically, the large language models typically do a lot of hallucinations. Stuff won't really work, and I don't like the way that AI writes paragraphs. I'm not against AI or large language models in general, but I don't think they're good content makers. I mean, maybe at least not yet. So I've had some fellow content makers who are like, "Oh yeah, we'll just make a new book. We'll just write a book. We'll use AI to write the book." I'm like, I don't think it's going to provide a lot of value. So this is all handcrafted, bespoke, artisanal, which is fitting because I live in Portland, Oregon, which is the capital of doing artisanal stuff. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 containers, all in 16 gigs of RAM. And it's called the Autobox. So if you're interested in following along, look up Autobox. Let's see if I can find the... yeah, it's called the Autobox. It's just a set of instructions to build this topology. So 2 spines, 4 leafs, 2 hosts, and an external router. It's very close to what Arista uses in their environments for their level 3 labs. Actually, most of their labs. They have more spines, and they have a slightly different layout. But they use Container Lab too, because it's such a great tool. And honestly, of the vendors, Arista has the best container. Because the other vendors make you use, Juniper has something called CRPD. It's not really a good analog to their switches or routers. It does some of this stuff and some of the syntax works, but some of the features aren't there. It's missing a lot of stuff, and there's weird licensing issues with it. So if you want to use their virtual switch, you can do it, but it's a VM, and it takes up a lot more RAM, takes up a lot more CPU. Same thing with Cisco. You've got the Nexus 9000 virtual machine, but it's a big virtual machine. Eats up like 5 gigs of RAM. Eats up not as much CPU as Junos does, but so this is a set of instructions on how to build a standalone Linux VM that will do all this. So that was one of the frustrations I had when I was starting out, was that there were bits and pieces of instructions here and there to build all this stuff, but there was no like one resource. If you do these things, you will end up with a virtual machine that inside of it has a bunch of containers and a topology that you can use to practice automation and Arista EOS, leaf spine, EVPN, VXLAN. So that's what that does. So I'm using CEOS 4.30. There's a newer version out, but whenever there's like exams, they tend to be on some older stuff. So I just kept that a few versions behind. All right. So, and then you could use a more updated version if you wanted to. So it's everything's tested on this virtual environment. So I'm not testing on physical switches, at least not yet. They're harder to get access to, and yeah, so I'll just do that. All right. So the underlay. Topology, we just basically talk about the different topologies that you'll have. So the topologies devices is the nodes. So one of the naming conventions that I use is that there's leafs, spines, and potentially super spines. So I just call them nodes in the fabric. So the topology is nodes, leaf spines, and how they're plugged into each other. How many leafs, spines, and possibly super spines you have. How many connections are between them, etc. Generally, the topology will be leaf and spine. Every leaf will plug into every spine. The leafs will only plug into each other if they're in an MLAG pair, and the spines will generally not connect to each other at all. So the first thing I'm going to do in this session here is I'm going to make a diagram for this. And I think I've got something I can reuse. So another thing I'm doing is writing a troubleshooting EVPN VXLAN course. But so I've got this. I can use that. That'll work very nicely. There it is. So I'll put a section header here, topology, and a new slide. So when we're doing, so some of this will be design as well. Oh yeah, this is layer 2, not layer 3. Yeah, so I want to copy this one actually. There you go. So we really have two choices. Like when we're doing the topology, A couple of the choices we have are how many spines are we going to have? We don't have to have just two. So that's one of the biggest advantages over doing it the previous method, which would be what we would call a collapsed core. Arista calls it layer 2 leaf spine, where the gateway's on the spine layer or on the collapsed core layer. And when you do that, you can only have two of them. And that will limit, bring some limitations. So one of the things that it limits is how many, what your redundancy is. So if I only have two and I lose one, I've lost all redundancy. And I have 50% of my 40 capacity. If I have three and I lose one, I've still got redundancy. I can still lose another one and still forward traffic. And I've only lost a third of my capacity. So that's one of the big reasons why we moved to layer 3 leaf spine. Yeah. So, and then another choice we have in that topology, and this will affect how we cable things up, is are we going to do MLAG or EVPN all active? So that's MLAG. And then EVPN all active doesn't connect the leafs together. So in no case do we connect the spines together. The spines are never connected directly to each other. The only thing the spines are connected to is the leafs, and then maybe some super spines if we're going to be doing one of those other topologies. So, in fact, I've got. So I've been doing this so I have the graphics that I can put into the document here. So, for example, I'm going to create a folder here called 2 images, and then. So this is EVPN all active. Oops. Yeah, this is EVPN all active. And that's MLAG. Nope, darn it. MLAG. So with MLAG, we connect the devices to each other, the leafs and leaf pairs. Make that more. Then we do EVPN all active. They are not connected to each other. The leafs are not connected to each other at all. There we go. So that's the big difference between those two topologies. And then a third topology that we have is, well, not really a third topology. So this is a multi-pod, also known as a 5-stage CLO. And we have these pods here. So I'm going to get rid of this stuff. So these are our leafs, and they're different pods, point of delivery. So this will be pod 2. Now the debate is whether or not we call them pod as it's not an acronym, but Arista tends to use an acronym for it. So pod 1, pod 2. We call this a 5-stage CLO because it's 1, 2, 3, 4, 5 potential switches in between the two hosts, maximum. And that's where we do leafs, spines, and super spines. So I think we'll do that here. Call this MLAG pair. I just need diagrams I can put in the book. Another reason I'm writing this is that there isn't a book. There's a Arista Warrior, but as far as I know, that has not been updated to include EVPN VXLAN. Let's copy these so I can label them. And shift everything over so it's not right at the edge. All right, so that looks good. I'm going to use a program called Snagit, which is I've been using this for a while. I'll just do a screenshot here. Like that. So I'll save that. Yeah, so put it in there. 2 images. I'm going to call this leaf spine. I'll call that mlag. Save it as a PNG. So I think the fidelity will be better. So that's a PNG. And then I need to put an image in here. So image source equals 2 images. L3ls mlag.png. So now when I right click on this and I do open and preview, we'll see that there. Sizing wise, I'll just leave that for now. I'll figure out what I want to do with that. So, in some situations, there may be a third layer called the superspines, which would aggregate distinct sets of leaves and spines. So 3-stage CLO, 3-stage CLO networks also refer to some of these leaf spines where you have a number of leaves connected to a number of spines. And then I can look up in Wiki, look up, I think it's Charles CLO. Yeah, Charles CLO. So it's not exactly what we do, but we still call it CLO network. It's not CLOS. And I've definitely called it CLOS. But it is an engineer way back in the day, before modern data centers, of course. So as we have a number of spines, the number of leaves and spine scales pretty high. The limits are usually the number of ports a leaf has and the availability for uplinks. So I don't want to go too much into this because this is not really a design guide, although it could be. So maybe, for instance, a common. Let's look up. Let's look up 70 Arista.com. Just go to Arista.com. Go to products, product overview, product families. Looking for the 7250s, or 7050s rather, not 7250s. There's two common data center switches. It would be like the 7280 as one common one, and then there's the 7050. There's several generations of this. We're on the X4s now, it looks like. It just means what chip it's based off of. So probably the most common one is the 7050 CX. Oh wow, that is all right. So maybe not the 7050 X4s, X3s. So these are probably the most common. So it'd be 48 ports of 25 gig and then 8 ports of 100 gig. So I think this is probably, like, every vendor always has one switch, which is like the one everyone uses. So what is the difference between these two? 48Y C8. Generally we want 48 ports of 25 gig and then 8 ports of 100 gig. That's usually plenty. Let's do the oversubscription for this. So 25 times 48. And then we've got 800 gigabits. So divided by 800. 1.5 oversubscribed. That's not bad. That's in most cases that's perfectly fine. If you want to do no oversubscriptions, you can get this one, which has 12 ports. Yeah, so this one right here is 1-to-1 subscription. So yeah, we'll put that in there. That'll be fine. A common data center switch used for a leaf is the Arista 7050 X3. SX3. Which has 48 ports of 25 gigabit capable ports, SFP25, and 8 100 gigabit ports. So just to be consistent here. QSFP. Pretty common. The other one that I see the most common is, I think, one of the 7280s, which has the ultra deep buffers. but we'll use this one for an example. This switch would generally use the 100 gigabit ports for uplinks to the spines, and the 48 25 gigabit ports would be connected to hosts. This would mean a maximum of 8 spines, though generally 4 or less spines are used. Not always, but 4 or less. I don't really see a whole lot of environments that use more than 4 spines. I'm sure there are, but they're just not very common. All right. At least we'll generally split between a high number of... we already talked about that. Some leafs are unispeed, such as a 32 or 64 gigabit, 100 gigabit. This is a 32 port 100 gigabit switch, in which some ports are used as uplinks to spines and others are used for 100 gigabit downlinks to hosts. And of course, there are multiple 400 gigabit options now. Especially for spines. Let's use a common spine switch. Like a 64 or 100. Yeah, this would be a pretty good spine switch right here. The 76s use the Tomahawks. I don't know if this would be more popular than the others. 7060. Looking for 3200 gig ports. The 64 ports here. Mm-hmm. Spine switches are generally single speed, such as the Arista, which has 64 ports of 100 gigabit. interfaces. With this would generally limit the number of spines to 8 spines, though generally it's not common to have more than 4 spines. This would limit this would limit the number of spines to 8 spines, though generally it's not common to see more than 4 spines. With 4 spines, each 100 gigabit link on the leaf could be doubled up. So each spine would have 2 100 gigabit connections from each leaf. And another issue of the topology is MLAG versus EVPN all active. One of the considerations for topology is what method of multi-homing to hosts is going to be used. With Arista EOS, there are generally, with their EOS and EVPN VXLAN, there are generally 2 methods for multi-homing a host. Multi-homing is when a host is plugged into 2 or more devices, 2 more leaves. So if one leaf is down for maintenance or has any kind of failure, or a link fails, the connection survives on the remaining leaf. More traditional method for multi-homing is known as MLAG, or multi-chassis link aggregation. MLAG has been around for over a decade, almost 2 decades. Like, when did MLAG came out? For over 15 years. Might be 20 years. So I'm going to run it for over 15 years and is generally trusted on the Arista platform. Other vendors have different names for it, such as VPC, Virtual Port Channel, for Cisco, and MCLAG for Juniper. It means the same acronym, multi-chassis link aggregation. They just decided to include the C in the chassis part. The other option is using aspects of the EVPN standard called Ethernet segments, also known as EVPN all active. So there's a couple of different names for it. It's not generally, people have not been consistent with what they call it. And the two, I think I need to take a nap soon. The other option is using aspects of EVPN standard called Ethernet segments, also known as EVPN all active. This method has, with EVPN all active, there's no MLAG configuration on the leafs. With MLAG requires a peer link. So generally, two of the host-facing ports, not the uplink ports, as opposed to the uplink ports, to the higher speed uplink ports. MLAG requires a peer link, so generally two of the host-facing ports, all as opposed to the higher speed uplink ports, are dedicated to this peer link. The peer link is used to exchange table information. If a frame is learned on one leaf, it's shared with the other leaf in the MLAG pair. All right, I think that's good for now. There's no one really watching, so we'll go ahead and stop the recording and stop the streaming, and enjoy your weekend, everyone.